Hello, welcome to Dr. S. Sahid Bidar. In the last class, I have told you it does not work out like if you just go about the YouTube without going about any of the books. So it is mandatory before you come to the YouTube platform. What I'll prefer you is go for a book, read books, spend some time in the library. So the conventional method of learning is the best method. Now let's move to our topic, that is the steady state error. So as we have seen in the previous class, the steady state error in the time domain was given by the expression E of t was equal to R of t 1 plus GH. So this same thing, if we need to convert into the Laplace domain for the error, and I told you the steady state error E of t limit t tends to infinity will become 0. So this error will become 0 at a large interval of the time. For that, if you can revise the previous lecture of the transient response analysis. So here, if we convert the same into the Laplace domain, so we get in this form E of s is equal to limit s tends to 0 s r of s 1 plus g of s h of s. Now we are interested to understand. Last time I told you, if there is a body like a table, if I give it a force, so our force is mass into acceleration. So it moves from position A to position B. So the moment while it's moving is the state of transients. It has some velocity and there is some position change. So whenever there is a reference input we are giving to any system, a system can be anything. To any plant we are giving, plant can be your element wherein you are acting upon. It can be an engine of a car or an industry, and prior to the plant there is also your controller, and you have your response here, that is the output of the response, which you are again feeding back to the input, wherein here is your comparator that is comparing. So here you require a transducer or an sensor that makes the output similar to the input so that it can be compared. The thing is that if we should know the feature of this plant, for that purpose we should know what type of input should we apply, whether it will respond properly or not. In the electrical and the communication system, it's quite easy by the monitoring of the voltage and other factors we can, but when it comes to the electromechanical and magnetic systems, we definitely go for certain amount of the test signals. So the elementary test signals as input that we are choosing in the control system is the unit step signal. Unit step is one of the signals, wherein unit step, as we have already told, if it is a unit step, so the value of the step would be, and in the Laplace domain it is 1 by s. If it's a unit ramp, it would be t. In the Laplace domain it is 1 by s square. Similarly, the parabolic is 1 by s cube. Okay, this can be written as into a if it is not a unit step, and for a ramp it can be a into t. Similarly, for a parabolic input it can be 8t square by 2, which can be represented by 1 by s cube. So now we will see that how the errors are getting generated. Suppose we have a response, it's not a unit step, it's just a step input. So let's check out the response for the step input, how it would be and what would be the its. See here, if I take into the error equation E of s as SRS 1 plus GSHS. So what I do is that I give my input as a step input. So R of s as a step input, it is not a unit step, so it would be A by S. So now my input here is A by S. So it would be A by S into S divided by 1 plus G of S H of S. So this S and S gets cancelled, and I am left with E of S is equal to A limit S tends to 0, okay, 1 plus G of S H of S. So this is the limit S tends to 0. So here one, because there is no S term involved, so directly we'll move to this particular part. So limit S tends to 0. Here you can see limit S tends to 0, H of S, G of S. This limit h is a constant, and this is called the position error constant. How much there would be the difference in the position, okay, from A point to B point. And the corresponding error here, ESS, would be equal to A1 plus KP, as it is shown here. So the error to the step input is given as A1 plus KP. Now same thing if we have to see for the velocity input. So for that we will give a ramp signal. As I told you, by now you might be able to do it. It would be A by S square instead of that. So we'll put an symbol of A by S square here, as you can see. And similarly we will put here, instead of R of S, we will put A by S square. So one S term and one S term will get cancelled. So you are left with, instead of you are left with S and S term gets cancelled. So you're left with A by S, and you have here limit S tends to 0 plus S G of S H of S. So here this S term goes to 0. You're left with only this portion. This portion also goes to, you might be wondering why I'm applying limit separately. This is just to show that this term over here, this term is called the KV term. This is called the velocity error coefficient. This term in the denominator is represented by KV, and I can represent this function by A divided by KV, wherein the velocity error coefficient is S, G of S, H of S. Similarly, if you see here, yeah, you can see here clearly in this slide, you can go about it. Similarly, if you want to go for the ramp error coefficient, what you will do is, there, here you have to apply the term A by S square. The moment you are applying the term A by S square, what happens is that A by S cube. So you are applying A by S cube, and your original signal was S. A by S cube you are applying for R of S, and that is 1 plus G of S H of S. So now again you are left with this. So now the term that would be S, that would be A divided by, again this would be S square plus S square G of S H of S, and here this limit S tends to 0. Here S is tending to 0, so this term becomes 0, and you are left with this term that is called the acceleration error, K by A. So this term over here, which you are seeing here, S square G of S, is nothing but the acceleration error, which we'll be seeing in the next slide. So this is called the acceleration error coefficient, and it is given by, so it's clearly, you can see the error due to the unit step is EOSSS is equal to A divided by 1 plus KP. This is due to the step. Due to the ramp, you saw it is straightforward, A divided by KV, and due to the parabolic input, you saw the response is A divided by KA. So this is how the response you are getting. So these has been summarized in the table. You can look at the table, and these are the values of the different error coefficients. Now when we are giving this error to any plant, the plant will have a different transfer function. Now what do you mean by a transfer function and this approach is that, see, there are two things in a system. One thing is called the type, and another thing is called the order. Now if you look at this G of S H of S, basically G of S H of S in any system, you have G of GS 1 plus minus G of S H of S, where when this is the plant and plant gain, and this is the feedback of the system. Now one important factor over here you will notice is that if you are writing any system in this format, you have to write, okay, so the highest power of this S gives you the, so the power of S, which is separated from these polynomials in the denominator especially, will tell you the type of the system. Suppose if this J was 0, then I will say this is type 1. If it is J is equal to, sorry, if it is 0, then it is type 0. If J was 1, type 1. Similarly, if J was equal to 2, then I will say this is type 2. And the highest power of S, highest power of S in denominator will give you the value of, it will demonstrate the order of the system. So this is the difference between order and type. So now let's go to the steady state error and how different errors are acting to different types of systems. So let's go for the position error system. Now when we are going for the position error system, so look at the position error system over here. So this is for the type 0 system where s is equal to 0, there is no power of s. Basically here s tends to 0, so s power 0 is 1. So in this scenario we already know kp is given by limit s tends to 0, okay, g of s and h of s. So here if we substitute the value of s0, here also s0, 0 and 0, so we are left with in g of s, h of s value is given as just as k. So this is the value of k. And for the this error we already know ESSS is equal to a divided by 1 plus kp. So if we are applying a step response to type 0 system, so we will have a error, and error would be the magnitude divided by 1 plus kp. Now the same error if it is applied to type uh, suppose type 1 system. Now in case of a type 1 system, here you can look at the type 1 system wherein here there is the s power 1, so hence it is type 1 system. Again when we have to put, so in this characteristic equation we will put limit s tends to 0. Now if we are putting s tends to 0 here itself, if s is 0, so the value of s we have to put 0. So anything divided by 0 would give you the value of infinity. Here itself, no need to put here, down only you. So you come to know that Kp is equal to infinite. So now E of Ss would be equal to A divided by 1 plus, instead of Kp will put infinity. Anything 1 plus infinity would be infinity. Anything divided by infinity would be 0. So that means there is no steady state error for type 1 system. If your position, there is no, the position error is 0 in case the unit step response is applied for a type 1 system. Now same scenario if I have to do with the type 2 system, here also you see instead of s is equal to 1, what you put s is equal to 2, s square. Now if you are putting s square, again you have to put 0 over here, it will again become infinity. Here again it will be 1 by infinity. For type 2 also it means there would be steady state error would be 0, which is reflected in here for the position. Now let's go for the uh, that means this for unit step for type 1 and above systems there would be no negligible error, a very small error, and for type 0 there would be some amount of error. Now let's go to the understanding of the velocity error. So we already know that for the type see how the error is defined. For the type 0 system it's simple, your kp is equal to limit s tends to 0, g of s, h of s, and your kv is limit s tends to 0, s g of s, h of s. Similarly your ka is only the power of s is getting increased, limit s tends to 0, s square g of s, h of s. So here you note it's clearly the power of s. So here again if you have to put this value, so what you do is that you first of all you have to put here the value of in order to get the this value of kv, what you do is that in this characteristic equation, suppose here this is the value, you have to multiply this with s. So for type 0 system, definitely for type 0 system also you need to multiply with s. So you will see that for this is for the type 1 system. Now look at for the type 0 system. Type 0 system you have multiplied with s. So the value of g of s of s would be equal to 0, and your this error would be equal to a divided by 0. It would be equal to fine infinity. So again infinity. But for type 1 system, if you are dividing it with s over here, because this s power 1, so this s and this s gets cancelled, and rest you put this will become 0, this will become 0, this will become 0. So you are left with k, and here the gain of the system would be a divided ess would be equal to a by kv, which is some finite value a by k for a type 1 system. Now similarly for a type 2 system, again you see for type 2 system what you have to do here, the power would be s square, so it would be s, here the power would be, so for type 1 system if you have to write, what will happen for sorry type 2 system, it would be s square. So again and power of s is coming here, Again, this would be equal to infinity for type, see here, a by infinity for type 2 system. So velocity error would be 0 for type 2 system. Now, same scenario with the acceleration error. If you have learned for one case, another case becomes easy. Only thing for the acceleration error is this is s square g of s h of s. Only thing this you have to remember. Now for type 0 system, directly you have to multiply this, but here you have to multiply with s square. So when you are multiplying with s square and put the value of s is equal to 0, so this will become definitely a by 0. This will become equal to infinity. Now for type 1 system, again an s term will remain here. If you are putting it 0, this will become 0. Again it will become infinity. But for type 2 system, you see here, this is s square divided by s square into k. So this and this is getting cancelled. So this power of s is not applying. So there is, here you put 0, here you put 0, here you put 0, here you only thing the value remaining is k. So for type 2 system, ESS of would be equal to a by ka. There would be some finite value for a parabolic input, which you can see here. Now these are the tables how you can go for it. So I have summarized it. So you can remember also, and you can see for this thing, error coefficient for type 0 for position it is k. Okay, here it is 0 0 infinity k 0 infinity k, which we have just seen. Now let's go for a problem that has appeared in the GATE examination recently. So this is very interesting thing. Let's go about it. So the problem is, yeah. So a closed loop system is shown in the figure where k is greater than 0 and alpha is less than 0. The steady state error due to ramp input. So we know it is talking about the ramp. So when it is talking about the ramp, I'm sorry, let me go to the other slide. Yeah. So when it is talking about the ramp, so I know the input would be equal to a by s square. Okay. So this is the input that I will have to feed. And the transfer function over here that I have to notice is that, see, for ramp system, I know my error ESSS would be equal to limit s tends to 0, s g of s h of s, right? So here if you look at the g of h of s value, here they have directly mentioned it, and they have given this value to be equal to kv value to be equal to kv value be equal to uh, kv. I can write s into k s s plus 2, right? So here this s and s will cancel, okay? And if I have to calculate the value of this kb, what I have to put? I have to put limit s tends to 0 for getting the value of this error. So if I'm putting s tends to 0, what is my value for the kv? The value for the kv would be equal to k by 2. And I know for ramp type of input, my this error is given by, error would be given by ESS. As you can see in the previous slide, it is given by, it is a type of the system type 1. So if it is a ramp input, it's a by k. So you can see this is a type 1 system, okay? And I will be having the error a by kv. So what is a by kv? So my a by kv would be equal to, so this is my k by 2 value. So my input is alpha basically. So it is nothing but I have to write this s, okay. Uh, what is the error value? E of s is equal to, I told you how it is given. It is given as r of s, okay, into r of s plus, in the previous slide you can see that it is given here in the beginning. I will show you here. You can see that it is given as r of s 1 plus g of s h of s. Same thing I'm telling. Sorry, where it went. Yeah, here it is, 1 plus g of s, h of s. So what is my input here? My input happens to be alpha s by square. So I will just put my term this alpha s square, okay, and for my error the formula is into s, okay, and this is 1 plus g of s h of s. So what happens is this gets cancelled and I am left with limit s tends to 0. So this 0 goes plus limit s tends to 0, this value of s g of s h of s. So the value of s g of s h of s just now I calculated is nothing but my kb value, that is equal to k by 2. So this value would be equal to alpha divided by k by 2. So this is equal to 2 alpha by k. So my answer is this. Hope you have understood the discussion, but I request you to please follow certain books instead of blindly following YouTube and understanding, thinking that I'll understand everything. You have to read the text, develop the habit of reading if you want to succeed in life. That is my request to you before moving into any YouTube or some platform. Thank you very much. I'll end the meeting. Thanks a lot.